afternoon, good morning, good evening. Hi, Muzammil, how are you? Can you hear me?
Yes, I can hear you. I mean, there is some background noise coming, some music. Yeah, now it's
Yeah, okay, perfect. Thank you. Okay, I'm going to leave to share my screen.
Mhm.
Okay, perfect. This is the last. Okay, perfect. Thank you. Okay, perfect. Let's get starting with this webinar. Good morning, good afternoon, and good evening to our global community joining us from all around the world. Welcome to this international webinar organized by Karyotech. My name is Richard Zapata, and it is absolutely a pleasure to be your host and moderator for today's highest level scientific sessions. Before we dive into the core of today's presentation, I would like to share a few quick guidelines to ensure we have a smooth and seamless experience. According to the audio and video, please ensure your microphones remain muted during the presentation to prevent any background noise or interference. According to the question and answer sessions, we will have a dedicated question and answer sessions at the end of the talk. Please, anytime, feel free to type your questions or comments in the chat box. At the end of the presentations, I will read them out to our speaker later. And finally, according to the connectivity, if you experience any audio or video lagging, we recommend refreshing your browser or checking your local internet connection. Okay, today we are catering for a truly fascinating and cutting-edge topic in computational drug discovery. The webinar is PoseidonQ for fast development of machine learning based on QSAR Webapps. I'm going to introduce to our speaker for today. He is Muzammil Kabeer. Muzammil is a highly accomplished software developer specialized in CAT, artificial intelligence and machine learning. He's the brilliant mind behind MC-Doc, and of course PoseidonQ. Additionally, he is the co-founder of Pyrex. Particularly, I am a Pyrex user. He holds a master degree in pharmaceutical chemistry, bringing the wealth of expertise in building advanced tools for the scientific community. Muzammil, it is an absolute privilege to have you with us today. Thank you for accepting this invitation and for answering my email invitation. This was wonderful for me. Thank you so much for taking the time to share your knowledge and innovation with us. So the virtual stage is all yours. Please feel free to share your screen and take us through the presentation you have prepared for today. Welcome again, Muzammil. Thank you.
Just give me a second. Just give me a second.
Okay, perfect. Let me know if you can share your presentation. To the audience, if you feel free, if you feel comfortable, can you turn off your camera during the session, and later, maybe at the end of the presentation, you can turn it on.
I mean, first of all, I just want to thank Richard,
Thank you
for conducting such. I think a platform like this is pretty low. So I mean, this initiative is wonderful from your part. So especially for me as well as those who are participating in this session. So, introducing myself, I currently work as a scientific software developer in a company called Research, and PoseidonQ was one of my academic projects. But I mean, it's being used in industries as well. So, without further ado, I mean, I could just share my screen and show what it's all about.
Okay, perfect, Muzammil. Go ahead. I'm going to leave you the screen.
Okay, yeah. Is it visible right now?
Yes, I can see your screen, Muzammil.
Yeah, okay. So, uh, this is the PoseidonQ. This is our logo. So starting off with the basics. I mean, you might have seen this equation somewhere, in your high school or college in maths, obviously. So the function of x is what gives the y. So this is actually a rule which exists everywhere in the world. So so every quantitative and qualitative output, which is the y, is a result of certain factors. So there are certain factors going on in the other side, which gives out the y. So for example, I could give, like, for example, my height depends on the height of my parents. So so this is how everything works, right? So let me just give you another example. So the function of a phone, could lead to the rating of the phone. So the rating of the phone is dependent on the phone, and this phone could be divided into its features. Okay, the phone is, you could equate the phone as an integration of different features, like, for example, the phone's RAM, the phone's display, the phone's memory, the battery usage. Everything is certain parameters which represents the phone. So all these certain parameters could be equated to the rating of the phone. So so the idea is that how can we relate the parameters? So we actually have this thing called weights. So each parameter, could be optimized to find out the y, essentially. So this is actually used in a lot of areas. It's used in simulations, like, for example, in the scoring functions in the docking, because it's actually having weights which is optimized to the binding affinity data. And similarly, in QSAR, you have multiple different models, and all the models, we train the models with the data, and this data is used to optimize these weights. And it's actually, it's not as simple as this equation. This equation would work out for a linear regression model, but there are other models as well, non-linear models. So all these non-linear models, although it doesn't work this way, but it does prioritize features and how they affect the y. So basically, so let's take a look at how from the point of view of chemistry. Okay, so similar to f of x is equal to y, you could actually remove the x, and you just keep your structure, molecule structure, and you keep it on the other hand your activity. So this is what basically QSAR is. It's simple and it's evident in the name itself. So you are actually quantifying the structure-activity relationship. But you need to understand that you can't just give a compound and just the binding affinity data, and get the model to give out predictions. You need a way to make the machine understand the structures. So you might be probably knowing this by now. The chemicals or compounds could be represented by smiles. So it's a one-dimensional way of representing the compound. But usually this is not enough, right? Because you can't just give smiles to the model, because model doesn't understand that. You need to parameterize it. You need to parameterize it, just like the example I gave you. The phones, you need to parameterize it with the features. Similarly, the compound that you have should be parameterized into features. So we could do this in two ways. So one is a molecular fingerprint way, where each bit in your structure will be converted into binary vectors like ones and zeros. So 0 means that that particular bit doesn't exist, and 1 means it exists. So the other one is a much more global based way, which is molecular descriptors, so like molecular weight of the compound, like log p, etc., etc. So I mean, you might be asking or wondering what is the advantage of each fingerprint or descriptors. So the answer to that is, fingerprints actually could be used for interpretation. You could, map, the substructures to the binding affinity data. So that would make it relevant for a chemist. But molecular descriptors, on the other hand, usually works out well in regression models. And usually when you do the publication, people ask, models generated with both fingerprints as well as molecular descriptors. So that is how the QSAR works. You have this data, the smiles, and you parameterize it, and you find the relationship to the binding affinity data. So this is an example of how your input data would be. So you would have your smiles over here, you would have your binding affinity data. And it could be anything. It could be, QSPR, any sort of properties like log D. But today I'm gonna show you how you're gonna relate it with the binding affinity data. So the idea is that when you increase the number of data points, that much better your model will be, because the model understands different diverse sets of compounds. So in turn, your model is going to perform better because it's going to understand much more compounds and scaffolds. So yeah, so the purpose of the QSAR model is to predict compounds activity. That is obvious by now. But there are ways in which you could process, the Y-label data. Just like I mentioned here, this is the Y-label data. You could actually, process it and convert the QSAR to, to different tasks. So there are two tasks mainly. One is a regression task, which is exactly what I have shown here, where you give the binding affinity data. Most probably it's going to be in nanomolar range. So you need to normalize it into log values, because the reason why we are normalizing it is the same reason why we convert the marks into percentage or a CGPA, because it's much more easier for the model to understand the range. So that is the reason why we are normalizing the Y label, so that it's continuous and it's in a range. So that becomes a regression task. And similarly, I could actually change this into a classification task by keeping a threshold, like for example, 6. Then those above would be actives, and those below would be inactive. So that would change your task into classification task. So so that's about the data and the Y-label processing. But we need to understand one important thing which most people miss out on. So this thing is called applicability domain. So you need to understand the fact that your model is as good as the data. So suppose you train your model on a specific scaffold. You can't expect it to predict for other scaffolds because you don't because the model doesn't understand. Simple as that. So there should be a way in your QSAR model to specify this domain, because when for example, you might have used Swiss ADME or Swiss target predictions. Some kind of a QSAR model is going on there. So you would give, your compound for prediction and gives, this probability range, something like that. But there are certain models where you don't get this applicability domain. So that really reduces the reliability of the prediction because you just get the predictions. You don't know how your compound is relating to the data set where the model is trained on. So we need to look into the training data set and define a chemical space so that when the user gives a compound to predict, you could classify whether it's inside the chemical space or whether it's outside the chemical space. So the idea is that the compounds that you're going to give for predictions should be somewhat similar to the chemical space of which your training data is. You can't go beyond that. So there is a certain point, and we need to define this. So for fingerprints, we use a technique. You could use multiple techniques. But in PoseidonQ, we use tiny model similarity frequency distribution, to find out the median similarity, to define the AD. And there is, for descriptors, you have this thing called a boundary box, where you find out the minimum maximum of each parameter. So so this is how you do the AD definition. I mean, I could go in detail, but let's just continue with it. So why do we need? We need it for the reliability of predictions. So yeah, so now you might be understanding, okay, the function of the structure is what relates it to the activity. So I mean, if you would change a simple methyl group, it actually affects the activity of the compound. So this theory is what is being used for QSAR modeling. But obviously, we need to find the relationship, right? So that's where we would, be using things like machine learning models, deep learning models, to find the relationship between the parameters on the one side and the activity on the other side. So when we use the model, we also need to understand whether it's a good model. So how to validate your QSAR model? So to validate QSAR model, we have different metrics. For regression, we have R-squared and RMSE. So R-squared is simply showing how much powerful your independent variables are. I mean, independent features means the parameters like log P, molecular weight, and how much it can explain the variance in your binding affinity data. So that's pretty much what R-squared is, and it ranges from 0 to 1. And for the RMSE, it is a measure of error in your model. So this should be as low as possible. So for classification, the metrics are different. You have this accuracy where the predictions are right, but that in itself is not enough. You need other parameters to validate, metrics to validate your model, like sensitivity, specificity. And the reason why you need that is because sometimes your data might have 99 actives and 1 inactives. And if your model is unable to predict that 1 inactive, what happens is that the specificity would be 0. But that is not the reality, right? Because you only had 1 inactive, and your accuracy might be around 99%. But if you would use the specificity, you get a 0 if it's if the inactive was not predicted as inactive. So this accuracy is sometimes it's not that reliable. You need to see how well actives and inactives are predicted. So that is the reason why we have sensitivity to see how much positive predictions are predicted and specificity for inactive predictions. So MCC is a bit of everything. So MCC ranges from -1 to 1. So ideally, a cross-validated MCC of 0.5 might be good. I mean, the more it is, the better. So before validation, we need to split the data. So you suppose you have 100 compounds. So you need to split the 100 compounds into an internal set as well as an external set. So the external set is done at first. So you take out 20% or any sort of percentage out from the initial data set. Or you could use a separate data set. Anything is fine. So what happens in the internal data set? So suppose if I have in the internal data set 100 compounds, we do something known as cross-validation. So the picture below is an example of the type of cross-validation, which is known as k-fold cross-validation. So what it does is that if I give a k-fold split of 5, my data set would be split into 5 folds, 5 divisions. So each fold, inside each split, one fold would be separated out into test. The others would be the training. So this process keeps on repeating 5 times, especially if I give a k-fold split as 5, it would iterate for 5 times, and each time the test changes. And each time you get a cross-validation performance, whether it's R-square, RMSE, you get this performance, and you could actually average those and get a mean and standard deviation. So this is quite useful to know the stability of the model, and it would be asked in publications. So you would need a cross-validation mean and standard deviation so that the stability and the performance of the model, especially internally. So, but since cross-validation uses every data set for training, you obviously need an external set to be a pure test set. So what external data set does is that you need to understand how much generalization your model is capable of. So you could use this external data set to know that. And you would get the metrics as well there. So you would get the same R-square and RMSE. And you could compare the internal validation R-square and RMSE with the external validation R-square and RMSE. So this difference should be minimal as possible. So that is what validation is. So this particular statement that you achieved an accuracy of 100% is kind of ambiguous, since the thing is that 100% accuracy in chemistry is kind of a difficult task. So you can't expect an accuracy of 100%, especially if you have a huge number of data points, diverse set of data points. I mean, if you would have 10 or just a small number of data points, yes, it might be possible to have an 100% accuracy. But as you increase the number of data points and the model you're trying to build a robust model, the chances of getting an 100% accuracy is really low. And then I have seen some researchers where they they increase the training data set percentage and reduce the test set to like a low percentage. So what happens there is that your model is not getting tested. So the chances of inflation in the metrics is possible there. So the idea is not to increase the metrics. To be honest, the idea is the model should be usable, because so Yeah, so that is the idea. So because some people, reduce the number of data points to just inflate the metrics, and what happens is that the model is not usable because it's not it hasn't learned a diverse set of data points. So the other thing is the data leakage. I mean, data leakage is only possible if you use coding for your task. And the other thing is that 100% accuracy is possible if your problem is simple. People use machine learning for other tasks as well, not just chemistry. So you could see one graph below. So what is happening over there is something that we need to see. So there is a case. This is actually something of machine learning. There's a case of overfitting. So what happens there is that you have a small set of data points and your model actually trains it really well. So what happens is that it memorizes those so that it can't predict anything outside of that. So that is bad, right? Your model should be able to predict compounds outside that. You can't predict, too much outside. At least within a space, you need to, predict. So overfitting is bad. And underfitting is bad as well because it doesn't, learn the relationship of your compounds to the binding affinity data. So that is bad as well. What you would need is a good balance, and do not, memorize, the compounds. So PoseidonQ has this comparative analysis feature where you could, see, cross-validated metrics of each, models, so that you could decide on which model is better. So the thing is, it's really easy and fast to use. So if you're wondering how to download or install this PoseidonQ software, you would probably need to, go into the SourceForge. It's a website where PoseidonQ is hosted. So you could, just download the installer and install it in your system. It works in both Windows and Linux. And the main part is that this is not just for making a QSAR model. You could also translate the models into a personalized QSAR web app. So this is really useful because you could deploy it online, and you could, if you're doing some sort of publication, you could, give the link of this QSAR web app because it's free. It's free of cost. The deployment is free of cost. So I will show you that. I will show in the demo. It would be quick. So this is a publication of the PoseidonQ. It's published on a Journal of Chemical Information Modeling, and it currently has around 11 citations and downloads of around 1.1K downloads. So after this presentation, we're going to go into the session overview. We're going to do a session. It would be fast. So what we would be doing is that we would, collect the data. So PoseidonQ has integration with the Campbell database. So you could collect just by giving the target name, and you would get the data. So you don't need to get other data. Then we would, do the data pre-processing, which is happening inside the, software itself. So it won't be taking that much time. You just click on a button and it does everything. So then we know. We do the AD definition based on, the fingerprints or descriptors. We do cross-validation to find out which model is best for our case. We do an internal validation, to see the metrics. Then we would be doing external validation in the web app. Then we would, build and deploy the web app. So we would be deploying the web app in this session. So how to install? Just go into this URL provided, and you just click on the download button. That's it. So this is actually something that I just wanted to show, where these are where the downloads came from. So it has been downloaded all around the globe. You could see most of the downloads came from India, USA, China. So, next could be you. So let's just, start with the session. So where is my cursor? Yeah. So yes, this is the software right here. I hope it's visible. And yeah. And first of all, I would recommend for people who are installing the software to put on a light mode instead of dark mode in your Windows, because it's not made for dark mode, so it gets ugly. So now, at first, what we would need, we need a data, right? So just click over here, and here you could type out your target, or PDB ID, or a Campbell target ID. Anything is possible. So right now, I'm just going to give a PDB ID over here. And I get some index. You could see it's DNA topoisomerase. It's single protein, so that is good because we are building the model specifically for a protein. And you need to see the organism. The organism is Homo sapiens, so that's good. So you just click over here, and you could see that the target index is enumerated. You could see the standard type. So what do we need? Do we need an inhibitory concentration, or excitatory, or inhibition constant? So I would go with the IC50, and then you just click extract. So you could see that the number of molecules extracted is 353. So one thing I wanted to show is the fact that you could see the length, and this terminal is where you could see the loading. So this loading was fast. I mean, the extraction was fast due to the fact that, I mean, it's cached. So since it's cached, it got fast. I mean, if the index actually had, 2,000 or 10,000 compounds, it would take much more time. So now, if I want to confirm whether the data has been staged, I could, go over here. I could see the data that I have. Could see I have around 353 compounds, and I could even add compounds here and save it. That's one possible way. You could add your own data. The other way is that you could take a template CSV and give it to fill it up and give it as a CSV with this button over here. The other way is you could even curate by drawing the compounds, add it up, and you give the nanomolar value it has. Anything is possible. I mean, if you have a QS property, you could give it over here. Yeah. So I could add as well other compounds. You could add, and I could transfer. So that gets added up. That overwrites the the staging file. But if you want to merge, you could merge it up here. And this is actually useful if you are using literatures to get the compounds to build the model. So this would be this can make the process much more faster. But today we're gonna just go with the Campbell dataset. So yeah, so I have already extracted. So yeah, so this part over here is really useful for the QSPR. So the QSPR, so if you press this, check this radio button, what happens is that your Y labels won't be processed by PoseidonQ. So you can process yourself. So that makes it easy for you to make a QSPR model as well. So since we are making a QSA model today, we don't need that. So this is where we need to assign the task. So I'm just gonna go with the regression, And then, you have the fingerprints, 70 different fingerprints. And you also have descriptors over here on the bottom. So I'm just going to go with the Morgan fingerprint right now. And you need to, keep this checked because I need an external data set. So from this the stage data set that I extracted, 20% would be, extracted out for an external validation set. So I would just click proceed, and let me just make a new folder. Let me just make a new folder over here. Okay, and I'm gonna save my external data set. So yeah, so right now the AD has been defined. So I have used Morgan fingerprint. So what happened is that you have this Tanimoto similarity pairs and the frequency. And in the x-axis, you have Tanimoto similarity, which ranges from 0 to 1. So 1 means it's really similar. So a pair is really similar. If it's 0, it means it's completely dissimilar. So what does this graph show? This graph shows that my data set that I extracted is highly heterogeneous in nature because it's skewed to the left, right? So that's why we got a median of 0.12, which would be used as an 80 threshold, while we would be using the model for predictions. So every combo that I give for prediction should pass this threshold, and that is for 6 neighbors. So that is how 80 works in PoseidonQ. I mean, if you're making models yourself in Python, you could, use your own ways of 80 definition. So here you could see all the compounds, and it has been converted to log values. Yeah, so you could see it's in a range from 4 to 9. And if you want details, you could just give it details. And I'm just giving a 6 threshold, so that I could see how much distribution my dataset have. So this is actually asked in publication. So you would need this plot. So you could say the plot by this. And you could see how much unique scaffolds it has. So there is around 132 unique scaffolds over here with the counts. So you could also see the minimum PIC50 and the maximum PIC50 within this data set. So this is also important as well, because in papers they would ask this part. This is actually to show the diversity of your compounds data set. So there is another feature which is explore. So I'm just going to explore it. Click explore. So this is something which will be really useful for you. So what happens is that all this data set would be projected into the 2D space with the gradient, of course. So if it's above 7, if it's yellow, it means it's highly active. If it's in the blue or purple, it's inactive range. So you could see activity clusters. So you might be wondering which is the x-axis and which is the y-axis. What is y-axis and x-axis? So the x-axis you could change. Currently it's in molecular weight. Then y-axis is in the log P. So here, what is the utility is the fact that I could, project my compounds into this space. So I could, draw a compound. Let me just draw a compound over here. Okay, I copy them, close it, and I space it over here, project. So what happens is that my compound gets projected. So my particular compound is in this space. So if you could see, the distance between the activity cluster, you could use this as a way to, find out or optimize your hits. So this is one. This is just additional feature. It's not, part of QSAR, but it's a way to, see the diversity of your data set. So once I have the data set, I could compare or feed the data set into models and compare with the metrics, right? So here I can specify the k-fold split, just like I mentioned before. I'm going to give 5. So low variance threshold, on the other hand, for fingerprints, it must be 0. Because in fingerprints, you don't delete parameters. You need to keep all the parameters, all the bits, you need to keep it because it's important. But in the case of descriptors, you could give 0.01 or 0.05. This is because, certain parameters would be similar all throughout the dataset. So we don't need that parameter in that case because it would be redundant and it would make the models worse. So I'm just going to give the 0, of course, and I'm going to keep the fingerprints as I have given in the 80, the same fingerprints. I could even change as well, to see which fingerprint is more suitable for my model. But then I got to change the 80 going back. But I'm just going to go with the Morgan right now. So this is some feature that you could, explore yourself. Sequential feature selection, which is, you just, you take 50 features outside from, suppose you have hundreds of features in the article descriptors. You use the sequential feature selection to select this 50 best features based on the cross-validation metrics. So this is something that you could explore because it takes time. So I'm just going to go with the default ones, and you could see the loading here. So you could see it's evaluating the models. So here I could see that the best model based on the RMSE and the R-square is NuSVR. Okay, because it got a cross-validated R-square of 0.71, which is good, especially in the case of cross-validation. So I'm just gonna save this table. With this could be useful in the publication where you have each model with the R-square mean with the standard deviation and RMSE mean with the standard deviation. So you also have this plot. You could save it, to give it in the publication, which is really useful for the reviewers to see why you made the choice of taking NuSVR as the model. So then here I could just go keep the NuSVR and the Morgan, and I could just click confirm. So here there is a feature for hyperparameter tuning with the grid search, but that would take time. So I'm just going to go with the default features because this is actually features of the model itself. The model itself has some parameters you could optimize. But here in this case, I'm going to go with the default one. So the model is built, and I can save the model in a directory. You could see the scatter plot here. I mean, it's good because this red line is the ideal line where the actual values and the predicted values are the same. So the blue dots are your test data points in the cross validation. So we take all the, basically it's everything because each fold has becomes a test once. So that's what is happening over here, and most of the blue dots, which are single data points of smiles or compounds, and most of them are inside the green or closer to the red line, which is the ideal line. And here you could see the internal validation metrics. Yeah, so you need to note it down, this internal validation for your publication. So you could take a screenshot or something and keep it. So then is the interesting part. So we're gonna build the web app. So I have the model with me. Actually, I saved it in a folder, right? I saved it over here. I show you. Yeah, I have saved it over here, and you could see I have this model.joplib. This is the model file. And I also have the scatter plot. which is saved. Let's see this kind of upload over here, and the tiny model similarity distribution. Everything will be saved once you give the directory for saving. Then I have the internal validation here. Let me just build a web app. So at first, I need to, I'm going to give a title, maybe Karyotech, PoseidonQ. Second, PoseidonQ. So I'm just going to view it. So it actually starts a web app, but this is actually locally in your system. I mean, we need to send it to the GitHub to make it online. So here I could give my smiles. So let me just give a random smile. I could apply, confirm. So here you could see that this particular compound is inside the applicability domain, and you could see the predicted PIC50 value. You could see the tiny model similarity with top 5 neighbors. You could also see where it's located in the TSNE projection of your training data set. So you could also see the multiple properties as well. You could give multiple compounds to prediction as well. So let me just give my external validation set so that I could see the external validation metrics. So currently it's loading right now. It might take a few seconds since we don't have much data points. So let's just wait for a few seconds till it, So what it does is that it predicts for you, as well as it predicts the validation metrics. So that would be the external validation metrics. So here you could see the R-squared RMSE, which is the external validation metrics, and you can compare it with the internal validation. So currently right now, let me just bring up yeah. So comparing the internal validation, external validation, actually the external validation is more than the internal validation, which is good. I mean, if the external validation is poor than the internal validation, that's when the problem is. So you would give this internal validation, external validation in the table for publication. That's how most people would do. And you could also, save this table as evidence. So here you could see the AD definition, whether it's inside or outside, the predicted values with the true values, and you would also get the mean tiny model similarity right here. So right now, so I just want to mention one more thing. Wait a second. Okay. So once at first, if someone clicks the view, what happens is that in the terminal, they would be asking the Gmail. So you would need to give the Gmail. So then the this app would be generated in the browser. So you need to give the Gmail. Since I have already given my Gmail here, that's the reason why it automatically just popped up. So now I need to build it. Okay, I need to build it. So I just click build, and then I'm gonna save it over here. So it's saved. So let me just go to the folder and see what happens. You have an app folder. So this is the app. It has all lot of files. So you need to actually upload this into the GitHub and then connect the Streamlit. So this could be done really easily. So I'm just going to show that to you. But before that, I mean, you could also, so suppose I close the PoseidonQ and I want to load the web app again to my PoseidonQ. You could load this app folder. So I have this app folder. You could load this. load this app folder, and it loads your web app, previous web app. So since I have already built the web app, let me just show you how everything works. Wait a second. Okay. So at first, after creating your web app, and you have this app folder, you need to have a GitHub repository. I hope that everyone here has a GitHub account. So you need to, if you don't have, create a GitHub account and create a new repository. So I'm just going to give a name here as Karyotech 123. Yeah. So then it should be public. Create repository. So it creates this repository in my account. Then I could use this URL. I could use this URL from my case. Then I need something known as Git. So that you could, install this Git with an installer. So what it gives you is you would get Git CMD. So I'm just going to show what it is. So you would get something like this Git CMD in your desktop. Then I need to go into, wait a second, I need to go into my directory. Need to check where it is. Oh, it's in here. So I could give CD and go to the directory. So I'm in this directory right now, and I need to go into the app directory. So the app is a folder that you would get after the PoseidonQ does its thing. So then is where you need to give the comments. So git init, git remote. So these commands are really easy. I mean, it looks overwhelming, but the thing is that it, currently there's AI and the other things. You just need to ask how I can upload it into, my repository. So here I have this command git remote add origin and given the URL that I just copied. Wait a second, remote add. Okay. I need to enclose them in. Okay. This is because I have a space in the username. So you need to, be careful of that. So then I would, add git add, git commit. Oh, git branch name, git origin main. Okay, wait a second. Please make sure you have the correct source repository exist. Oh my God, I gave the URL, not the right URL. Okay, so I need to repeat that process again. Wait a second. So yeah, so I have just sent all the files from the app, which is my folder in my desktop, to the GitHub repository right now. So you could see all the files just reached my repository. Yeah, so this is actually the Python file, which is a web app, which is automatically generated from the PoseidonQ, so that you could, give it, connect it to the Streamlit. So then you need to, make an account in Streamlit. So you just type in into Google Streamlit and make an account, and there you could, create an app for free, and you need to deploy the web app. So it's like deploy a public app from GitHub. So here I have already connected it to the GitHub, so I could directly see all the repositories in my in this space. So let me just take a look. Yeah, this is the one. So here, predapp.py. Yeah, it exists, and I could give a domain name. So I'm just gonna give Karyotech 1, 2, 3, 4, 5. Okay, as the URL for the web app. Then I need to change the Python version to 3.11, which is very important. Otherwise, it will fail. Then you just need to click deploy. Sorry. So what happens is happening here right now is that your files are getting uploaded into the Streamlit. Your repository is getting connected into the Streamlit. So you would have a web app that too with this URL. So the URL that you would get here. So it's loading up right now. So it will take quite few minutes. I mean, I think maybe a minute. So it's already done right now. So you could actually, I could actually copy paste this URL so that you could, see. You could, I mean, if you would go into this URL that I have posted in the chat, you could actually go into this web app and use it. So this is how you could actually, and this works as well. So let me just demonstrate it. So let me just first just give the URL somewhere. Yeah, so it works. So then I could, just draw some random compounds. So now you could publish it. You could give to your fellow researcher, or you could give it in papers, and you could, publish somewhere, and the users could use this URL and use your QSAR app. So yeah, so it's working. It gives everything. Yeah. And if you want to make changes and you know a bit of Python, you could always change things here. It is actually a bit long, but I mean, you can figure it out. I mean, if you want to customize it, to make it unique, you could do that. So yeah, so that is it for this session. I hope I have covered everything. And if there is any questions, I mean, I could answer few of those. Hello.
Hello, yes, thank you. Thank you so much, Muzammil, for such an insightful and brilliant presentation. It's a truly amazing to see how Poseidon streamlines the fast development of machine learning-based QSAR applications. I confess that only I arrived before the app creation in your software. I can scale to the next steps, but now with this tutorial, I feel that I will be capable to create my web with my target.
That's a good news. That's a good news.
Okay, so now we will open the floor for our question and answer sessions. To everyone in the audience, please feel free to type your questions right here in the chat. Or if you prefer, you are more than welcome to unmute your microphone and ask Muzammil directly.
Okay, so may I ask?
Yeah,
Yes, go ahead.
it's audible. It's
Okay,
audible.
so actually myself, Dr. Pawan Gupta, I am from India and working as a
Yes.
associate professor in SPKM and MIMS Global University. So
Oh,
it's a very
nice.
actually excellent tool which I've seen and how nicely actually explained by Dr. Muzammil. So my question
Thanks.
is that the data, whatever you taken directly from PDB,
I mean, you could actually give PDB ID in that browser space. I mean, it's not taken from PDB database. It's like Campbell has this feature where you could, give this PDB ID and get the related compound data. It's
okay,
possible.
okay. For the one particular protein, we have a multiple PDB IDs. So it will automatically extract all the PDBs in
Uh,
particular target.
I
Or,
I I mean like I don't know about that, but I mean I could look and let you know. But there is actually an option where you could just give the target name, like for example, Cox or Maubi, and gives you this index which is there in the Campbell database.
okay.
So you could use that, and just like I showed, the single protein and the protein family, you could, use single protein so that you're sure that it's just a single protein. But the PDB ID, I think it's connecting to a specific index. I mean, the PDB ID is just, to make things easier. I don't think it has an entry for PDB ID.
Okay. Actually, if I see the some protein like ABL1 kinase, so when I see the PDB, it's having more than 100 or something like that I found actually. So that is
In the
why,
software,
yeah, yeah. So PDB explained by
compounds,
this PDB by
compounds or index.
no, only just PDB ID with the different co-crystallized ligand.
Okay.
So
I mean, it's better to give the protein name instead.
okay.
This I did, just to make things faster. I mean, I usually give like MAO-B
Mhm.
or Cox. That's what I used to give, and it would give the index, and you could see the protein name, and you could choose one of those.
Mm. Is it possible to give the multiple targets modeling? We can do that.
Yeah. I mean, multiple target in the sense, each target would be a separate model, right? And
No,
you build the web app.
like
Or
some multiple single molecule is binding and having activity against the multiple proteins.
dual inhibitors.
Dual or actually like more than two, more than three sometimes.
Mm. I mean,
So
usually we make a dual inhibitor model by creating single model for each target.
okay.
You make for one target one and the other target one, and then you should make a web app. I mean, you could actually change this web app to host two models. Like you could do some coding using AI or something,
Mhm.
make changes in this spreadapp.py, which is there behind this PoseidonQ, and then you could actually add two models behind and make the prediction. So you give the compound and two models would predict. So you would get two predictions.
Mhm.
This would be useful for dual inhibitors, and that too with the SHAP analysis. Like you could do something called SHAP analysis where you could map the substructures and how much they contribute to the binding affinity. So they would, if you have two models for each target, what happens is that, and you have the SHAP as well, which you would get in the Python. What happens is that it gives the prediction, not only the prediction, it also gives the substructure mapping and how much contribution they have to the binding affinity. So you could see this two SHAP plots of two models. So you could make a decision then, because you're making models for two different targets. So I think that would be useful in that case. I mean,
Okay.
yeah.
And this particular data set limit is there in this tool, data set. If you have a 10,000 data,
Yeah, I mean, that's a good question, actually. That's a good question. Because the thing is, this tiny mode of similarity, sometimes it runs, exhausts the RAM. So that is one case that I have seen where the app crashes. But I think I have solved that issue right now. So I haven't tested out it, to be honest, with too much compounds. The max I have went is maybe 10K compounds. That's it. Yeah.
Okay. So this whatever you given presentation, some tutorial or some that guidance,
Yeah,
will
yeah. There is actually one in YouTube. I mean, I could share the link
please,
in this
please.
chat. I mean, if that is okay. Yeah.
Because why I am asking actually, my PhD scholar is working on some the different model on the cancer drug. So
That's great.
I
So I just want to publish that model publicly so that everybody can use it by using your app. So I found very fantastic this particular tool actually. So
Thanks.
that will be that will be great for others also and my scholar also. So we have 1,000 of molecules and toxicity data also we are having. So that is
Mm.
my plan actually to create a app or that we will allow the public to use it and predict their molecules.
Yeah,
So
that's
that's why
actually a
I'm
good
yes,
idea. I
yes.
mean,
So that's why I'm asking if we have some tutorial that how to make a model and how to transfer in GitHub and JIT or Streamlit, whatever
mm,
you told. So I will ask my scholar to explore all those things actually. So it will be great
yeah,
help for us. And meanwhile, if you will also support in these particular things, then it
yeah. I mean, I mean, sure. Why not? I mean, you could contact. I mean, I
yes.
could also give the tutorial link. I mean, I do not know that this tutorial has this deployment.
Okay.
I mean, deployment. I think it's not that difficult right now in this era because you have this AI and other things. I mean,
Yes, yes,
you
yes,
just give how to upload and you could just
yes,
do it.
yes. No. Yes, yes. Actually, I have experience on Comfa and Comsia. So it's a 15-year back. Actually, I explored.
Oh,
At that time, it was actually Sibyl tripose force field
mm.
we used. I don't know nowadays what we are calling, but Comfa, Comsia, I used actually.
Oh,
So
it's 3D
yes, 3D QSAR,
QSAR.
3D QSAR,
3D.
contour maps, all those things, and I am also using Glide actually, Phage also
Mhm.
I am. So that is the thing that this new things is coming and it will be good for the others also. That's why I am very much
Yeah.
interested in the different data, not in the single cancer actually, multiple cancer molecules I am having. So it's a
Mhm.
huge like why I ask because
Which
we have a sorry.
Can I ask a question? Sorry to interrupt.
Yes, yes.
Which university are you from?
Sir, I am from SVKM and MIMS Global University. It is in India, and
Which
I am a
state?
associate.
Which
Yes,
state?
it's Maharashtra.
Maharashtra. Okay.
Yes, so I am working in that as a professor in pharmaceutical chemistry department.
Oh, nice. Okay, nice, nice. Okay.
So it will be great actually if we have some work together sometime and we have some something we make good thing for the publicly people can use it and they will get a benefit in their study also.
Yeah, yeah. I mean, sure. I mean, you can contact me. I mean,
Yes, yes,
I'm free.
definitely.
I mean, yeah.
Yes. So can you give this link actually in tutorial link in
Uh, yeah. I mean, I could copy paste that in the chat.
Thank you very much, Dr. Pawan, for your participation in these
Yes,
wonderful questions.
yes,
So the
yes.
webinar
Actually,
is, yeah,
no, no. Actually, I will also actually very helpful if my college is having some online training. If my scholar, we have a lot of student here working in PhD and masters. So this
Okay.
will also they will get benefit actually.
Yeah, I mean, I could do an online session. You are asking for an online session, right?
Yes,
Or-
yes, 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 yes.
Yes, I mean that would be. I mean, I'm free right now, so
Yes, yes,
I can do it. So
yes. I will let you know, and definitely I will contact you.
mhm.
Mhm.
Yeah, yeah, sure.
So
Yeah,
you pasted, sir?
yeah. I'm just going to paste it right now.
Okay.
Thank you, Dr.
Yeah.
Pawan,
I mean, it isn't much detail, but I could, if you reach out to me, I could, explain, make it detailed much more.
Okay. So, okay.
Does PoseidonQ incorporate target protein structural information, or is it purely? It's ligand based. I mean, QSAR is ligand based approach.
Mm-hmm. Mm-hmm. So, mm-hmm.
Yes.
Go ahead, Dr. Pawan. Go ahead. If you have another
Okay.
question, please. You
Okay,
can do.
so this particular tool is also using some, deep learning and something other also algorithms you incorporated in it.
Machine learning.
Yes,
It's
deep learning. Yeah. Yes.
actually machine learning models are much better for QSAR predictions. I mean, there are many studies confirming that, even comparable to the deep learning models. The machine learning models are, I mean, especially the random forest is really good model, XGBoost. Yeah, I mean, that's enough. And then the next important thing is the fingerprint or the descriptors that you choose. So that is what, shows what your molecule is. So that should be correctly chosen.
Okay, so later on you are planning to incorporate some SVM, random forest decision tree.
SVM is
And
there. Everything is
okay,
there. Everything is
okay,
there in this
okay,
model.
okay. Everything is there. Okay.
Yeah,
So,
yeah.
so this is window based or it is a Linux?
Both. It's actually in both Windows and Linux.
Okay.
In Linux, it's a Debian file, so you need to
Okay.
install with Debian.
Okay. So it will be actually I will practice and I will explore. If anything is there, then definitely I will contact you regarding.
Yes, of course, of course.
Okay.
Yeah, I
And
mean, why not?
yes. So thank you very much for this nice actually sharing this particular tool and demonstration. So definitely I am getting benefit actually in. So thank you very
Yeah,
much.
why not? Why not?
Thank you.
Welcome, welcome.
Thank you.
It's a pleasure for me,
Yes.
to have.
Okay.
Yeah.
So I will actually contact you. Maybe your contact detail where I register actually there. It is already available.
I mean, it's I could give my. I mean, do you have a LinkedIn? So I could,
Yes. Yes. Yeah. Yeah.
yeah,
The
I could.
same name, Pawan Gupta. You can actually.
Yeah. I
Yeah.
will reach out to you. So
Yes. Mm-hmm.
yeah,
Okay. Thank you very much, Dr. Richard and Dr. Muzammil, for the nice actually session. Thank you.
thanks.
Thank you, Dr. Pawan, for your questions. Just for a reminder, this webinar is being recorded, so I will to share the link when this webinar is available in YouTube. So please feel free to write your questions here, please. So Muzammil, I can do questions, maybe.
Yeah. Why not?
Yes, I have the opportunity to read your paper about your software. So there you mentioned that the training of the machine learning is we prepare with 80% of all ligands retrieval from Campbell, and the remaining 20% is for the setting. So this 80% is fixed or is random.
I mean, the thing is, this is just for the external validation. I mean, you could uncheck that, and you could choose a completely different external data set. I mean, that's possible. I mean, we just fixed it, just to make it simple. I mean, we don't want the user to go through changing a lot of parameters. So the 20% is actually fixed for the test.
Okay, perfect. Thank you, Muzammil, for this this answer.
Yeah, I mean, you could uncheck those, uncheck, and then get another external data set, which can be 30% of the. I mean, you could do it anyway, like.
Yeah. Because I mean, for instance, if different users are exploring the same target, for instance, me and two another researchers more are investigating the same target, maybe the same 80% of all the data sets would be training in this machine learning software, or maybe it would be different. For instance, my computer would be the 80%, and another researcher would be the another 80%, and so on. Or for all the researchers will be trained with the same 80% of the data set collected from Campbell in this opportunity.
I mean, I didn't quite understand, the purpose of that. I mean, why, separating it to other researcher? I mean, why is that?
I don't know, maybe, for instance, if I want to publish in a manuscript in the particular target, for instance, if I publish this article, I'm going to publish the data, the NCE and R square and other parameters. And so it will be the same for the next
Yeah.
or
I mean,
the same target.
yeah, I understand. I mean, if you would use the same data set, that is the case. I mean, usually people publish either. I mean, there are certain ideas that you could implement. Like, I mean, if it's just a single target model, the chances of publication is really low, to be honest. I mean, if that's the case, you need to make a whole pipeline like docking, QSAR, MD simulation. I mean, then you could publish that paper if it's a specific target. But QSAR alone with a single model, that won't be publishable. And especially if you're using Campbell dataset, you need to have your own dataset, and maybe you should do prospective validation, synthesize those and have a bioassay. Something like that should be there. Otherwise, everyone else could do the same thing, so it doesn't become research anymore. So, yeah.
Okay, perfect, Muzammil. It's more clear after your answer.
Thanks. Anyone else?
Okay, anyone else maybe can do a questions for Muzammil?
So one more question I will ask.
Yeah, sure.
Actually, yes. If we sometime actually we have a lot of active molecules, and we don't have a sufficient inactive molecule in the data set. So is it possible that we can use decoy as a inactive molecule in the QSAR?
I wouldn't recommend using decoy, but there are people who use decoys and get good results. But in the software, I mean, one way I would suggest is that you have a lot of actives, right? I mean, you could divide these actives into highly actives and less active. You could actually paste the threshold somewhere where that after this point it's really good. So what happens is that you have this classification model, and this patterns in the highly actives, and the moderate active ones the would be in the other class. So I think if you would make something like that, it would be good. I mean, that's just an opinion, but I wouldn't recommend decoys because it isn't experimentally validated. So
Actually, recently I made a model from the, some deep cam or RD kit using, uh,
hmm,
so
decoys.
yes. So I
I
actually
think
what
you
I,
build conformers, and
no, no, no.
did
Actually,
it
what I
do
did,
3D? Yeah.
actually, I taken some active molecule from the repository for the particular
Hmm.
target. And then there is a one website actually, Dude Decoy something. So you just put
Yeah,
your,
yeah.
yes, so you just put your smile, it will generate the decoy in a smile notation. So one
Mm-hmm.
molecule maybe 50, sometime 30, they are directly generating whenever you giving the input. So what I did
Mm-hmm.
actually that I used those decoys and build the model.
Mm-hmm.
So I used different algorithms, random forest, SVM, XBoost, linear regressions, everything I use actually, 15 method I use actually.
Okay.
So, and different split actually technique I used, like
Mm-hmm.
20%, 30%, 40%. So I don't know. I didn't publish that particular paper till now, but
What is the result like validation?
result,
Is it good?
yeah, it is having, that external prediction, if you see, or internal prediction, you see, hardly if we have a 300 decoy, only hardly the bad prediction, the decoy is having, 20 or 10 or something like that, they are predicted active. So
Mm-hmm.
I found actually the accuracy of the model to identify the active molecule is reasonable.
Mm-hmm.
Otherwise, it should be value should be zero actually, because they are
Mm-hmm.
decoy.
Yeah, yeah. I mean, that is the thing. Like, this decoys should have a certain chemistry, and
Yes, yes. Actually,
how would you do that?
yes, what they claimed actually that they have some, physico-chemical properties like structure. They have a similarity and with some difference in the physico-chemical properties.
Oh, okay, okay, okay. I
So
mean,
decoy,
but still, that y values in the decoys is is it
zero.
might be predicted or something, right?
Yes,
It's
yes.
not
So
experimentally.
yes, so but I didn't use actually fragment. I used descriptor.
Mm-hmm.
So that's why I asked actually for if you have such experience. That's why I shared actually that some decoy we can use or not, because I never seen such paper that people used decoy as a inactive data set in their model.
I mean, if you can validate those and get good results, then why not? But I mean, the questions will come surely
Yes,
to
yes, definitely.
prove the chemistry
Mhm. Yes, yes. Yeah.
from the reviewer.
Yes, yes. Reviewer may ask. So that's
Yeah.
why I ask if you have had a such experience actually. That's why I asked.
No, no. Currently, as of now, I'm not looking into that. So
Okay. Mhm.
I mean that is something that we have to explore, obviously,
Mhm.
because we
Yes.
can't have all the data to
Yes.
train.
Yes. Yes.
So
Mhm.
we need to
Mhm.
have some way.
Yes. Yes. Okay. Thank you. Thank you, madam.
Yeah, you're welcome.
Okay, perfect. Thank you so much, Muzammil, for your time, for your brilliant answers, and for sharing your incredible work with us today. And a huge thank you to our wonderful global audience for your active participation and great questions. So before we close this webinar, I would like to share with you my screen. Okay.
Thanks. Yeah. Certificate of
Yes,
completion.
Muzammil, this is a certificate of appreciation for you from
Yeah.
Karyotech and for my person. This is a certificate of appreciation to Mr. Muzammil Kabeer for his distinguished contribution to the keynote instructor on the webinar PoseidonQ for fast development of machine learning-based QSAR web apps. Karyotech recognized his commitment to academic excellence and valuable support in training the next generation of researchers in computational drug design tools. This is for you. I will send you in your email this certificate of appreciation.
Thanks.
And thank you so much, Muzammil, for accepting this invitation.
Thanks, Richard.
Yes, thank you to the audience for your participation. Before we close this session, please, I would like to take a picture with all the participants. So please, if you are comfortable to open your camera for this final screen. Yeah, thank you. I am seeing you. Thank you. Thank you. The claps for you, Muzammil.
What happened?
People are
Okay.
clapping claps for you in the
Yeah. Okay.
Dr. Pawan, nice to meet you and nice to see you.
Thanks, Pankaj.
Yes, sure. Thank you. Share, please share whenever I have such type of the interaction, please.
Thank you for your participation. This is the picture, the final picture. Another one, please. Yes, thank you everyone for your participation. Thank you, Dr. Pawan, for your questions, and thank you, Muzammil, again for accepting this invitation
Thanks.
and for the webinar that you shared with us today. Thank you.
Yeah,
Okay.
thanks. Thank you, everyone. Bye.
Okay, I see you all for the next time. Please check our social networks and LinkedIn for the next webinar. Thank you to everyone. Bye bye. See you next time.